Hi, this is a video about closed system energy conservation problem, and this is one of the exam problem, and one student have asked me to take a look at this one. So let's see. They said the device has 0.4 kilograms, so I'm gonna write it down what's given. And initial state 1, it is saturated vapor, so it's gonna be water, and initial temperature is 200 degrees Celsius, and the work is done to the system to increase the temperature. So state 2, temperature T2 is 300 degree, and pressure now is 0.5 megapascal. And since there's no heat transfer, so Q is equal to 0, and need to find out how much work done to the system. Okay, so for this problem, we know it's a closed system, and but it didn't really tell us if it's a rigid tank or constant pressure. So we're gonna go back to our original first law equation, which is delta U equal to Q minus W. Okay. So in that situation, Q is equal to 0 because it's adiabatic, and they want us to look for work. So in that situation, this work is just going to be equal to negative delta U, and delta U is final minus initial, so that situation work is U1 minus U2. Okay, then now we're about to look for U1, U2. That's kind of the direction we're going. So finding internal energy, specific internal energy at state 1 is 200 degrees Celsius, and it's saturated vapor. We're gonna go to 200 degree, right? Let me see, it's 200 degree. Okay, so table A4, all right, table A4, 200 degree. We're going to come to this one. That's our table A4, and we're looking for UG, so it would be this column right here. And I have 2594.2. 2594.2. That's going to be our U1. Okay. Then, because U1 is equal to UF at UG at 200 degrees Celsius. Let me just double check, make sure I read read the right one. So this is UG. Okay, good. Now we're gonna look for U2. U2 is 300 degree and 0.5 megapascal. So if we go to table A5, 0.5 megapascal, that's gonna be basically 500, right? 500 kilopascal, and the saturated temperature is 151. However, here your temperature is 300, way greater than that, and then therefore we know it's superheated. So we go to table A6 and look at this particular pressure, which is 0.5, and temperature is 300, and we want to read the U. Okay, so let's look at it. U is this column, and I have 2803.3, so that's going to be our U2. 2803.3 and kilojoule per kilogram. So knowing that, we can bring it back to this equation right here. We have U1 as 2594.2, U2 as 2803.3, and then we'll have the unit of kilojoule per kilogram. Then let's take a look. 2594.2 minus 2803.3, that will give us negative 209.1. Okay. However, since this problem gives us the mass, so here is a small w, which means work by mass, and here we're going to use mass times negative 209.1. Then our mass is 0.4 kilogram, right? So we're going to put the 0.4 times negative 209.1. Let's see what would we get. Times 0.4, and I have negative 83.64 kilojoule. So the work done is this value, and the negative value means it's work done to the system, right? Because the work done by the system is positive. All right, so that's for this problem. It's first law, again, we do not know it's rigid tank or constant pressure. As a matter of fact, it's none of them. So we're going to go back to this original equation, delta U equal to Q minus W. All right, hopefully that helps, and I'll see you next time. Bye.